Hello and welcome. We finish now our storage and discharging technology video section for chemical energy storages with giving an overview on power-to-gas systems. And we start with power-to-gas hydrogen systems. The charging is done by water electrolysis, and that can be alkaline electrolysis, membrane electrolysis, and high-temperature electrolysis. Again, the water electrolysis reaction is given here, two parts of water in a liquid form. After the electrolysis process, we have two molecules of hydrogen and one of oxygen. In natural gas grids, hydrogen can be added to methane, but only up to a few percentage points. The challenge is the compatibility of hydrogen with several components in the natural gas grid infrastructure. Hydrogen is required in certain industry processes. Here, for sure, it is meaningful to directly use the hydrogen and not go in a further process. But coming to the power-to-gas methane systems, here hydrogen generated by electrolysis is converted to methane either chemically or biologically by means of carbon dioxide. And here we have added the Sabatier reaction. The CO2 plus 4 times of hydrogen then is converted into methane CH4 and 2 parts of water. And methane has the advantage of having a higher energy density than hydrogen. And of course, methane directly can be integrated into the natural gas infrastructure, so there is no limitation as we have seen with hydrogen. On the other hand, by the further conversion step, again we lose efficiency. That means the efficiency is again decreasing. Here we get a very good overview on how that system with the gas storage can look like. On the complete left side, we have the renewably powered generation, for example by wind, solar and others. And of course, we try to directly use them in the electrical grid. And also the gas power plants can produce electricity. But when we have excess electricity, then we can use that electricity via electrolysis to produce the hydrogen here. And in a further step, when we add CO2, that can come from the atmosphere, from waste, from biomass and so on, in a methanization, we can produce then natural gas CH4 and release water. And this methane, this natural gas, can be fed to the natural gas infrastructure, and the extraordinary large gas storages can also be used then to store renewable generated power or the gas resulting from the power. And then when we discharge it, we again can use this gas and operate in our gas power plants, or we operate them for heating, or we use them in the transport sector. And so we have a closed loop for our future energy supply system. The carbon dioxide sources, to repeat, it can be from air, but the concentration there is quite small. It can be from biogas plants. The CO2 can come from gas purification plants. It can result from gas emitted by coal power station, that is not anymore a green source, and from gas power stations and also from industry emissions. And there we need to consider that we are not doing greenwashing with these processes. But now to end up this complete section with gas storage and with the discharge mechanisms of the gas storages. Some questions. For how long already existing natural gas storages could cover the German electricity demand? Which discharge technologies for gas storages do you know, and in which energy sectors are they applied? Up to which concentration hydrogen can be added in the natural gas grid? How can the existing natural gas infrastructure be used for power-to-gas systems? Is it possible to save carbon dioxide emissions by power-to-gas technology? What are advantages and disadvantages when you compare power-to-gas with hydrogen and power-to-gas with methane? So thank you very much for your attention. Bye bye.